Hello, welcome to Unit 6. On day 1, we're going to revisit graphs of first and second derivatives. We did this in Unit 4. This is what we did before Halloween. And we looked at graphs and we drew, we looked at graphs of functions and we drew the graphs of the first derivative and second derivatives, noting what was important to us. So again, the first derivative is the slope of the original function. So when f prime is equal to 0, then there's probably going to be a minimum or a maximum. These are called critical points, and we'll get more into those on day 2. When f prime is positive, that's because the function is increasing. When f prime is negative, that's because the function is decreasing, and we've talked about this before. F double prime, the second derivative, is the slope of the first derivative, or the concavity of the original function. So when f double prime is equal to 0, that means we have an inflection point. When f double prime is positive, because it's concave up, and when f double prime is negative, that's because the original function is concave down. So let's look at drawing some graphs, and these are exactly the graphs that we did before. I really haven't changed them. I'm going to have to shrink them up a little bit, but the idea is that the slope on this graph becomes the y value on this graph. So if I look at this graph this whole time, this slope is equal to a positive number. Specifically, it's a positive 2. So I can draw a nice horizontal line at y equal a positive 2. Then I can look at, let me choose pink. Again, the slope of this graph will be the y value of the next graph. So this slope is always 0, so I always have to draw a graph that's always a y value of 0. That's how we go from f to f prime to f double prime. Now that's a pretty easy function. Let's look at something that's a little bit more work. Let's look at this graph. What's really key to me is that I want to note this max point right here because this slope is equal to 0. On this side of the graph, I have a slope that is equal to positive, and on this side of the graph, I have a slope that is negative. So right here at x equals 1, I have to have a x-intercept, because that is where y equals 0. And then I have to have a graph that has positive y's, 0, negative y's, and we'll get into more details on maybe what the steepness is going to be, but it would be this graph, because if you look on this graph, I have positive y, 0 for y, and then negative y. So again, the slope here became the y value here. And then if I do slope here becomes y value on the next graph, well, you can see that this slope of this f prime graph, it has a negative slope. So I'm just going to draw a horizontal negative y value. See, the y value here is always negative because the slope there is always negative. And then we can really talk about what does it mean to go from the original graph to the second derivative. Well, the concavity on this graph is going to be the y value here. If you notice, on the second derivative, the y value is always negative because the concavity here is always negative. And we'll go back to the third graph, and we did these before. We did these a few weeks ago. They're not really any different than before, so I'm noting the mins and maxes, because this is where the slope is equal to 0, and those become the x-intercepts on these graphs, so it's like negative 1/2 and 3. I have a positive slope, a negative slope, and a positive slope. So I should have something that goes positive 0, negative, back to 0, positive. If you notice, these y values are positive, these y values are negative, and these y values are positive, and it matches. And then I could find the min on this graph, which is right around here, like 1.5, and over here I have a negative slope, and then I have a positive slope. So we go negative, 0, positive. These y values are negative, these y values are positive to match a slope. And even more importantly, this x-intercept here, because f double prime does the concavity, it should go concave down, inflection point concave up, and if you pay close attention, right around here at 1.5 is this inflection point. Okay, let's try these on our own. The first graph, f, to f prime to f double prime, I'm going to go from slope to y values and then slope to y values, and I'm going to pause the video and you can see what I do. So you can see I went from f to f prime to f double prime. I took the slope here and made it the y values here. Slope was always negative, y values are always negative. And I looked at this slope. The slope was always 0, so these y values are always 0. And we talked about taking derivatives that we always lose a degree of x, and this is x to the first power, this is x to the 0 power, and then this is just 0. So as you can see, I started here with the slopes, and I took those slope values, positive, negative, 0, and I drew them here in red. And I took the slope of the red, I drew them, took those values, I drew them here in pink. And these values here, like negative 3 point something and negative 1.5, those probably should be the inflection points. So if you go over here, you can see that I'm drawing these black slashes. These are the inflection points. Concave down, concave up, concave down. And again, if I look at the powers, this is probably an x to the 4th power, this is an x to the 3rd power, and this is an x squared. Okay, stuff we've done before. F prime is the slope. F double prime is the concavity. The slope of this graph is positive because it's going uphill, and the concavity is concave up, positive because it's being curved up. Lousy plus sign, but you'll survive. This one, the slope is positive because it's increasing, and its concavity is down because it's curving down. The slope was negative, and it's linear, so it's 0 concavity. There's no curvature going on. Okay, we've done this graph before. This is when it is above the x-axis, and that would be from, let's see, from here to here, from here to infinity. There are actual arrows on this. It's going forever. It's not stopping. So it is above the x-axis from -5 to -1 in union with 3 to infinity. F prime is greater than 0. This is when the function is increasing. And I would say here and here are good key points. So I would say from -infinity to -3.5 it is increasing in union with 1.5 to infinity. And then finally, this is where it's concave up. I would say probably right around here is a good inflection point. So it's concave up from -1 to infinity. So some of the stuff we're going to do the rest on this day's notes is a preview for day 2, because we're going to use functions and factoring, and hopefully you can factor an x squared as an x and an x. I need a positive 2 and a negative 5 to give my negative 3 in the middle, so I get x equals negative 2 and x equals 5. Again, oh, I see x's everywhere, so I got to take an x out, and then I could factor even more. And I get 3 solutions. I have x equals 0, x equals negative 2, and x equals 6 are my 3 solutions. And I should have 3 solutions because it's an x to the third problem. And maybe one's a little bit harder because I have a 2 here. I don't do the whole Xbox method. If you have to do it, we can talk about it. But I look at this and I'm like, well, I'm going to do plus 1 and minus 5. And I could check it. I quickly check. And I'm like, well, 2x times x is my 2x squared. Negative 5 times 1 is my negative 5. And my outer is positive 2. And my inner is negative 5x. And I get what I want in the negative 3x. I can set these equal to 0. And I get this x is equal to 5 over 2. And this x is equal to negative 1. And I can go back and do my number lines. We did these before. This is why I did them for this unit. I have my x-intercepts equal to negative 1/2, 2, and 4/3. I'm going to make my number line. Put them in order. Negative 1/2. This is 0. 4/3. And 2. And my leading term is equal to 2x times 3x. I get 6x to the third. If I pay attention, positive 6 means I go positive, no bouncers, negative, positive, negative, alternate. X to the third means the two ends are opposite. If I look carefully here, I want the negative values, so here's a negative and here's a negative. Negative infinity and negative 1/2. Union 4/3 to 2. That is my solution. I'm going to do the same thing here. My x-intercepts are negative 1, 3, and negative 4. Special. There's a bounce. Here's my number line. Negative 4, negative 1, and 3. That's a bounce. My leading term is equal to x times x squared times another x. I got 1x to the fourth. That's a positive 1. So it's going to go positive, bounce back to positive, alternate to negative, go back to positive. X to the fourth means both ends should be the same. And I want positive numbers, including 0. There are my positives, so I have negative infinity to negative 4 bracket, union negative 1, and I could go including 0 all the way to infinity. Well, now I maybe have more difficult ones here. Well, the first thing I should realize is that it's an x cubed problem. I should have 3. So when I factor this, I can take an x out. I get 2x squared minus 5x plus 3. And I factor again, 2x and x minus 3 plus 1, because I want a negative 5 in the middle, and I can check. Negative 6 plus 1 gives me my negative 5, so my x-intercepts are 0, don't forget the first one, negative 1/2, and 3. My leading term is given to me at the beginning of the problem, 2x cubed, so I can make my number line of negative 1/2, 0, and 3. There are no bouncers here. Positive, negative, positive, negative. I want the negative values. They're here. So when I do the negative values, I get... Ooh, did I factor this wrong? I did factor this wrong. Wow, I'm not paying attention. This is bad factoring. I'm going to have to start all over again. Oh well, that's what happens. I'm not redoing videos. I want a positive 3. I did a negative 3. That's not right. Okay. Still x. 2x, x, less than or equal to 0. I have to have I either have to have 2 positives or 2 negatives to get a negative 3, so it's going to be negative 3 minus 1. And now when I check, I get my negative 2, I get my negative 3, so I get my negative 5x. So I do have, again, this one, x equals 0, x equals 3 over 2, and x equals 1. There we go. Bad factoring, see? You don't pay attention. It's easy to make mistakes. These are my x-intercepts. Oh, the leading term is still 2x cubed. So I do have positive, negative, positive, negative. That didn't change because there are no bouncers. I still want the negative values. So there are my negative values. So it's negative infinity to 0, union 1 to 3 over 2, or 1.5. Oh, this next one, a little bit more difficult. I can't take an x out of this. Synthetic. Need to use synthetic. So my p's over q's, I really only care about this guy. I'm going to use either plus or minus 1, 2, 3, or 6. I'm probably going to avoid the 6. It's probably my least likely choice. So my first set of synthetic I'm going to use. Actually, I did this with Sarah today. She just guessed 2. She put in her coefficients. And 1 came down, 2, negative 2, negative 4, negative 3, negative 6, 0. Look how happy we are. And then we actually tried something else to begin with, and it didn't work. So we tried, I think we tried 3 next. I'm going to try negative 1 next. I get, bring the 1 down, negative 1, negative 3, 3, 0. I'm so happy. So when I factor this, I have x minus 2, x plus 1, x minus 3, less than or equal to 0. My x-intercepts are 2, which I knew from the box, negative 1, which I knew from this box, and 3. My term I know, which is just 1x cubed. I can make it my number line, negative 1, 2, 3. Here are my zeros. It is a 1x cubed. There's a 1 here, so it goes positive, negative, positive, negative. There are no bouncers. I want all the positive values. So they're here, including 0. Well, I really want all the negative values. I'm not paying that close attention. Let me grab my eraser. These are positives. I want the negative values, which are here. Oh, just not drawing well today. So my negative values are negative infinity to negative 1, including 0, bracket, union, bracket 2 to 3. That's my result. Well, how about factoring when we have an e to the x with it? It's not as hard as you think. They both have e to the x, so I could take an e to the x out of here. And what's left over? 2x minus 5. Is that equal to 0? So what I'm doing is setting both things equal to 0. E to the x is equal to 0, and 2x minus 5 is equal to 0. That's an easy one. X equals 5 over 2 is the solution. And when does e to the x equal 0? Well, the e to the x graph looks like this. So e to the x never equals 0. It gets really close, but never there. E to the x is always positive. So I'm going to do the same thing over here and take out an e to the x. E to the x, I have 2x squared minus 5x minus 12, and I'm doing my inequality. So e to the x, and I get 2x, I get x, I need, let's see, a negative 4 and a positive 3, and I think I do get my negative 8, positive 3, and I get my negative 5. Again, I don't have to worry about this. Always positive. But these I solve. I get x equals negative 3 over 2 and x equals 4. I'll make my number line negative 3 over 2 and 4. My leading term is 2x squared. That is a positive 2. So it goes positive, negative, positive. And I want the positive results. So negative infinity to negative 3 over 2, union 4 to infinity.